Today we are going to tackle a concept that often intimidates beginners, but is actually incredibly straightforward once you visualize it. Balancing chemical equations. If you have ever felt confused by all the numbers and letters in chemistry, don't worry. As the graphic brilliantly shows, balancing an equation is exactly like balancing a seesaw on a playground. Let's break down everything happening in this helpful laboratory scene. The golden rule. Conservation of mass. Look at the very center of the seesaw, right on the blue fulcrum. It says balance, conservation of mass. This is the absolute golden rule of chemistry. The law of conservation of mass states that matter cannot be magically created out of thin air, nor can it be destroyed. Every single atom that goes into a chemical reaction must come out on the other side. They just rearrange themselves to form something new. The left side, the reactants. The left side of our seesaw holds the reactants. Think of these as the raw ingredients you are putting into a recipe. Hydrogen. Notice the large glowing blue number 2. This is called a coefficient. It tells us we have two separate molecules of hydrogen gas, H2. Because each individual molecule is made of a pair of atoms, the two connected blue spheres, simple math tells us that $2 times $2 gives us a total of 4 hydrogen atoms, oxygen. Next to it, we see a glowing blue number 1. This means we only have one molecule of oxygen gas, O2. It is made of a pair of red spheres, giving us a total of 2 oxygen atoms. If we look at the colorful tracker below the seesaw, we have a total starting inventory of 4 hydrogen atoms and 2 oxygen atoms. The right side, the products now. Let's look at the right side of the seesaw. These are the products, which is the final result that gets created after the chemical reaction happens. Water, H2O. The ingredients from the left side have rearranged themselves into water. We see a large red number 2 hovering above the products. This tells us the reaction produced 2 complete molecules of water, counting the atoms. Look closely at those 2 water molecules. Each one has 1 red oxygen atom sandwiched between 2 blue hydrogen atoms. If we count them all up across both molecules, we find exactly 4 blue hydrogen atoms and 2 red oxygen atoms. The balanced equation, because we started with 4 hydrogen and 2 oxygen, and ended with exactly 4 hydrogen and 2 oxygen, our seesaw is perfectly leveled. No atoms were lost, and no extra atoms were mysteriously created. In formal chemistry, we write this visual process out as a chemical equation, 2H, 2 plus O2 and right arrow. 2H2, the biggest takeaway for a beginner is understanding the difference between the numbers. The large numbers in front, the 2, 1, and 2 in the air, are the ones you are allowed to change to balance the seesaw. The tiny numbers, the $2 and H2 or O2 are permanent. Changing them would change the actual chemical itself. By adjusting only the big numbers, you ensure that both sides of your chemical equation always remain in perfect harmony. We are going to tackle a concept that often intimidates beginners, but is actually incredibly straightforward once you visualize it: balancing chemical equations. If you have ever felt confused by all the numbers and letters in chemistry, do not worry. Balancing an equation is exactly like balancing a seesaw on a playground. Let us break down exactly how this works. The absolute golden rule of chemistry is the conservation of mass. This rule states that matter cannot be magically created out of thin air, nor can it be destroyed. Every single atom that goes into a chemical reaction must come out on the other side. They simply rearrange themselves to form something entirely new. Imagine a seesaw. The left side of our seesaw holds the reactants. Think of these as the raw ingredients you are putting into a recipe. Let us say we are making water. We start with hydrogen. We have a large number 2 in front of the hydrogen, which is called a coefficient. This tells us we have 2 separate molecules of hydrogen gas. Because each individual molecule is made of a pair of atoms, simple math tells us that 2 times 2 gives us a total of 4 hydrogen atoms. Next to it, we have oxygen. Since there is a number 1 in front, we only have 1 molecule of oxygen gas. That molecule is made of a pair of atoms, giving us a total of 2 oxygen atoms. So our starting inventory on the left side is 4 hydrogen atoms and 2 oxygen atoms. Now, let us look at the right side of the seesaw. These are the products, which is the final result that gets created after the chemical reaction happens. The ingredients from the left side have rearranged themselves into water. We see a large number 2 indicating that the reaction produced 2 complete molecules of water. Let us count the atoms in those products. Each water molecule has 1 oxygen atom sandwiched between 2 hydrogen atoms. If we count them all up across both water molecules, we find exactly 4 hydrogen atoms and 2 oxygen atoms. Because we started with 4 hydrogen and 2 oxygen on the left, and ended with exactly 4 hydrogen and 2 oxygen on the right, our seesaw is perfectly leveled. No atoms were lost, and no extra atoms were mysteriously created. The biggest takeaway for a beginner is understanding the difference between... Let's break down these 2 graphics. Building carbon chains. The alkanes, the first image takes us right to the lab bench to build 3D molecular models. In these types of models, the black spheres represent carbon, C atoms, and the white spheres represent hydrogen, H atoms. By linking these carbon atoms together into chains, we create an entire family of molecules. Methane. This is the simplest hydrocarbon, represented by the formula CH4. It consists of a single central carbon atom surrounded by 4 hydrogen atoms, ethane. By connecting 2 carbon atoms together and surrounding them with hydrogens, we get C22H6. Butane. The hand in the graphic is finishing a longer chain composed of 4 carbon atoms, giving us the formula C4HR10. Counting in chemistry, the mole in our previous lesson, we looked at how balancing a chemical reaction is a lot like measuring raw ingredients for a recipe. But how do we actually measure those ingredients when atoms are too tiny to see? That is where the second graphic comes in to explain a brilliant chemical concept. The familiar idea, dozens. When a baker makes a batch of cookies, they do not buy or count eggs one by one. They group them into dozens. 1 dozen always equals exactly 12 items. The chemical concept, moles. Because counting individual atoms is impossible, chemists use a massive grouping called a mole. 1 mole equals exactly $6.222 times 10^23 particles, atoms or molecules. This giant figure is known as Avogadro's number. Chemical recipes. Let's look at the formal chemical equation we previously used for making water. 2A jars, 2 plus O par 2 right arrow, 2H, 2O. Instead of just saying 2 molecules of hydrogen, chemists read this recipe as 2 moles of hydrogen plus 1 mole of oxygen. Yields 2 moles of water. It is the exact same grouping concept as a baker using dozens of eggs. Just looking at the pH scale, which helps us understand whether a chemical substance acts as an acid or a base. The pH scale typically runs from 0 to 14 and acts as a measuring stick for how acidic or basic a liquid is based on its ions. Let us break down the details of this colorful scale, so your text-to-speech software can read it smoothly and naturally in a continuous narrative, right? In the center of the scale is pure water with a pH of exactly 7. It is perfectly neutral because it has an exactly balanced number of hydrogen ions and hydroxide ions. Anything falling on the left side of the scale, meaning numbers from 0 up to almost 7, is acidic. These acidic solutions have a higher concentration of hydrogen ions. If we look at everyday examples, they get increasingly acidic the lower the number gets, with milk sitting around a 6, coffee at 5, vinegar down at 3, and lemon around a 2. Conversely, anything on the right side of the scale, spanning just above 7 all the way up to 14, is basic, which chemists also call alkaline. These basic solutions have a much higher concentration of hydroxide ions. Common household cleaners often fall right into this range, like soap sitting around a 10 and bleach hitting a 12. By understanding the shifting balance of these invisible hydrogen and hydroxide ions, you can easily determine exactly where any liquid belongs on the acid and base spectrum.